Okay, we did some problems where energy was conserved. Okay, now we want to look at how do we account for energy considerations in terms of like a bookkeeping tool when we have non-conservative forces such as like a friction force. So here I have something sliding. Okay, so here's the ground. Okay, so this thing sliding across the ground. And this force here, that's my friction force. This thing's sliding to the right. Okay, and so it's moving here. So it has some kinetic energy. And then here it's stopped. Okay, we know it's stopped because the final kinetic energy is 0. Remember, kinetic energy is 1/2 mv squared. So if there's no kinetic energy, remember mass can't be 0, so that means v is 0. Okay, so we want to ask ourselves in this case, is energy conserved? Did the energy change? Well, for energy to be conserved, the change in energy has to be 0. Okay, if I look up here, change in energy is final minus initial. Okay, so my change in energy is final minus initial. So my change in energy was minus 100 joules. So the energy decreased by 100 joules. 100 joules of kinetic energy were gone. Okay, so energy was not conserved. So in this chapter, we would say 100 joules of mechanical energy were dissipated by the kinetic friction force. Now, where did that 100 joules of kinetic energy go? Well, the mug gets hot and the table gets hot. Okay, so if you take something and you slide it across the table, you're going to generate heat. So for example, take your hand, slide it across the table a bunch of times quickly. Okay, your fingers are going to get warm, the table's going to get warm. So the book calls that an internal energy. You might remember that from a chemistry class. So that's a thermal energy. So that thermal energy produced when that thing slides across the table, that's not a mechanical potential energy. Meaning, as that thing slides, it stops here, so the cup gets warm, the table gets warm, okay? So there's nothing stored. I don't get any type of motion back. I can't take the same cup, put it in the oven, heat it up, and then put it on the table and expect that cup to now move back off to the left. Okay, so that's not a reversible process. So the kinetic friction force is a non-conservative force. There isn't any energy associated. There's no stored energy associated with the kinetic friction force. So that energy is lost in the form of heat. So we can say that the work done by that non-conservative kinetic friction force is minus 100 joules. Remember, the reason it's negative is because the definition of work, so the work done by kinetic friction, is that force times the distance through which it moves times the cosine of the angle between them. Okay, so the kinetic friction points to the left, that's up here, and it's moving to the right, and the angle between those two vectors is 180 degrees. And the cosine 180 degrees on a calculator is minus 1. So remember, any force that's opposite to the direction this thing is going, okay, that force is going to do negative work because the cosine of any angle that's bigger than 90 degrees is negative. Okay, so the work done by friction in that case is negative. Okay, so that kinetic friction is a non-conservative force. There's no potential energy associated with the friction force. All the work done by friction is lost in the form of heat. Okay, so so when we say lost, I mean that kinetic energy is transformed into thermal energy, but that thermal energy is not a mechanical energy. You don't keep getting it back as potential and kinetic, potential kinetic. It just dissipates into the air. Okay, so here's the same cup. Okay, so moving across the surface. All right, so the kinetic energy started at 100 and wound up to 0. So the kinetic energy changed by minus 100 joules. So the change in kinetic energy is minus 100. Okay, now the potential energy, okay, PE, the potential energy doesn't change because this thing is on a flat surface, so it's not going up or down. So the change of potential energy is always mg times the change in height. The height didn't change. So there's no potential energy, or mechanical, I should say, gravitational potential energy associated with this problem. So if I look at the change in energy, well, that's 0. Okay, so the kinetic energy up here, kinetic energy change is minus 100. So there's my minus 100 joules. So the change in energy, okay, mechanical energy is minus 100 joules. The energy decreased by 100 joules. So started at 100 joules of kinetic, and now it's all gone. Okay, so we can ask, is energy conserved? Is the change in energy zero? No, change in energy is minus 100 joules. So that means energy is not conserved. Okay, when I say energy, I mean this word energy in this chapter means kinetic plus potential. Okay, so mechanical energy is not conserved. Okay, that 100 joules was converted to thermal energy. The mug got hot and the table got hot, and then that dissipates into the air. So what we can do is we can modify our energy expression, okay, to include any type of loss due to the kinetic friction force as this thing slides, and any other non-conservative forces, such as your finger pushing something, okay, a string pulling on something, all right? So we had previously conservation of energy, okay? That only holds when you have conservative forces. The only conservative force we had was gravity, right? You drop a ball, it's all potential up here, hits the ground, it's all kinetic, okay? But now we want to take into account what happens when we have resistive or friction forces, okay? So a non-conservative force can increase or decrease the energy, all right? So for example, if I have something here on the ground, okay, and I'm pulling it with my hand, okay, that pulling force, that's a non-conservative force. Okay, my hand force doesn't have potential energy. So in this case, the kinetic energy is going to increase. So this non-conservative force actually increased the energy, made it go faster. Okay, here, if I throw something, okay, across the floor as it slides to the right, I have that backwards kinetic friction force. Okay, so here I have a non-conservative force decreasing the energy. The kinetic energy is decreasing because it's slowing down. So a non-conservative force can speed it up, okay, like a string pulling something, or it can slow it down like a friction force. Okay, so now what we can do is we can modify our energy expression to include work done by non-conservative forces. So to modify it, we put in that term. So that says that the only way that the energy can change is if there's a non-conservative force that comes by and does work. So these are the exact same pictures I just had on the previous page. So here I have an object, maybe it's your glider, you had a string attached to it, okay? So this force P, that's a non-conservative force. It can make this thing go faster and increase the kinetic energy. Okay? So in this case, the energy does change because this non-conservative force is doing work. Over here, okay, here the kinetic energy is decreasing. It's slowing down because that non-conservative force, kinetic friction, okay, is changing the energy to decrease it and slowing it down. Okay? So this expression here, okay, is a modification of conservation of energy to include the situations when energy is not conserved. Okay, and that's why I like to say this is like a accounting 101. Okay, so if something is conserved in some cases, it's a bookkeeping tool. Okay, but now that we have non-conservative forces, we can't say it's conserved, but we can say we can account for all of it. Okay, so here's the situation, a similar picture we had. So here's this thing going fast, and here it's going slow. Now how do we know it's going slow? Remember, kinetic energy is 1/2 mv squared. So if it's 300 joules here and 200 here, that means that the speed decreased. Okay, but it's still moving. Okay, now I want to know, is energy conserved? Is E final equal to E initial? Well, the final energy, I just made up a number, is 200. Initial energy is 300. Okay, so did the energy change? Yeah, so the energy changed. It decreased oops, yeah, it decreased by 100 joules, went from 300 to 200. Okay, so is the change in energy 0? No. Change in energy is minus 100 joules. Okay, and that's because there was a non-conservative friction force, that one right there, that did work. Right, so change in energy is minus 100 joules. Okay, now remember the work done by the kinetic friction force is negative because the angle between the friction force and the direction it's going is 180 degrees. Okay, and the definition of work has that cosine. The cosine 180 is minus 1. So the expression we had before, okay, change in energy, okay, is equal to the work done by non-conservative forces. Here, kinetic friction did minus 100 joules of work, and that means the energy decreased, or the change was minus 100 joules. Okay, so we're not saying it's conserved, but we're saying that we can bookkeep it because we can know all the different things that added energy and removed energy. Okay, let's say same situation. This thing's sliding. Okay, now is it going faster or is it going slower? Okay, well, kinetic energy is 1/2 mv squared, so m's not changing. And here the kinetic energy is 300, and here the kinetic energy is 300. So that means the speed's the same. So it's going at constant speed. Okay, now here's the expression that we're working with. Okay, now did the energy change? Well, remember this E is kinetic and potential. Okay, we're not dealing with potential because it's not going up and down. So my change in energy is final minus initial. So K final minus K initial. So that says the change in energy is 0. Okay, so the energy is right up here. The energy up here is 300 joules. And the energy over here is 300 joules. Remember, energy is kinetic plus potential, but there's no potential in this problem. Okay, so the energy, okay, didn't change. Okay, the mechanical energy didn't change, all right? But we still have kinetic friction on the floor. Okay, so the work done by kinetic friction is still minus 100 joules. Okay, so that kinetic friction force is still generating 100 joules of thermal energy. Okay, so the cup and the floor gets warm. Okay, so we go back to our expression. Okay, we said that's our go-to expression. Up here, change of potential energy is 0. But the work done by non-conservative forces is minus 100 joules. So there's something wrong. This says 0 is equal to minus 100. Okay, and that doesn't make any sense. We have to ask what's wrong or what's missing from that picture. So I have 0 joules, energy didn't change, I have 0 joules here. Friction did minus 100 joules of work, so the only way to make the left side equal to the right side is I'd have to add 100 joules of energy. So where did 100 joules of energy come from? What's missing in the picture? So I have the same picture, okay? So what explains it is I actually have some external force, okay, your hand force, pushing on the cup to keep it moving. Because remember, V is constant. Okay? Kinetic energy is constant, so V is constant. So the only way that you can push your book across a table at constant speed, or the only way you can have your book move across a table at constant speed, is you have to have your hand behind it. Otherwise, if it's moving, you take your hand away, it's going to stop. So that means there has to be another external force, right? That's a non-conservative force, okay, that does work. Okay, so again, that's a non-conservative force because the only conservative force we have is gravity. Okay, so your hand force, or if there is a string attached to this, pulling it, that would be a non-conservative force. Okay, so now we can account for this expression because we know that even though the change in energy was 0, and kinetic friction did minus 100 joules of work, the hand, okay, had to do 100 joules of positive work to keep that thing moving at constant speed. So now I have 0 on the left equals 0 on the right. Okay, so this includes the work done by all non-conservative forces. So even though the analysis of this chapter seems kind of long, and we looked into definition of kinetic, potential, and work. This one expression allows us to solve all of our energy problems. If there's only gravity, okay, if you only have a gravitational force acting, then that term would be zero. Energy is conserved. But if you have friction, then that expression includes friction. It includes things like the hand up here. So this is going to be our go-to expression. We're going to use this expression for all of our problems in this chapter. Okay, now this one we did in the force chapter. Okay, this was the jet car. Okay, it left skid marks for about, I think, 6 miles. All right, and I knew the initial speed, and I want to find the coefficient of kinetic friction between the tires and the ground. And I said, for all practical purposes, let's simplify this and say that the tires are locked and it's just skidding. Okay, so it's skidding this whole distance. Well, if you look back in the notes, I think that's before, way before spring break. I had posted this one, and I showed how to do this one with the 5-step method. Okay, but Newton's laws are. We use Newton's laws in kinematics to get this expression. Okay, so we're going to use this and see what makes it different from the last way we did it. Okay, we want to find mu sub k. So remember, mu sub k, the only place mu sub k shows up is in that expression. Okay, so somehow it has something to do with kinetic friction. So here's the car when it applies the brakes. Here's where it stopped. So I showed it while it's skidding. Okay, so you have normal force points up, mg points down, kinetic friction force points backwards. All right, so I'm starting with this expression. Okay, and then change in energy is final minus initial, so I wrote that. And then what I did, because I didn't want to deal with a minus sign, is I brought the E initial over. I just brought it over there. Okay, now I'm not worried about gravitational potential energy because it's not going up and down. Okay, it's not rising in height. So the change in height 0, so my potential energy, my change of potential energy or my potential energy is 0. It's not part of the problem. Okay, so now I'm going to look at each term. So my E final is kinetic plus potential, final. E initial is kinetic plus potential, initial. And then I have that term. Okay, now the things I can cross out, final kinetic 0, because it stopped. Initial potential, final potential is 0. Because essentially, I'm saying potential energy, I'm saying potential energy is 0 at the ground. And it doesn't move up above or below the ground. So final kinetic 0, final potential 0, initial potential 0, because it's still at ground level. So all I have left is I have 0 on the left, I have kinetic, and I have the work done. Okay. Remember, the work done by the non-conservative force, that's our kinetic friction force. So I need to calculate the work done by kinetic friction. Okay, remember the work done is the force times the distance to which that force moves times the cosine of the angle between them. So in that picture up there, kinetic friction points to the left, car's moving to the right, angle between those is 180 degrees, cosine of 180 is minus 1. So the work done by kinetic friction is minus F sub k times x. So that's what I'm going to put right there. Okay, so I have 0, okay, initial kinetic energy plus work done by friction, so there's my 0, kinetic energy, work done by friction, remember it's a negative, so be careful. I threw this over to make it positive, okay, and then kinetic friction is always mu sub k times the normal force, all right, and you could look at that picture, okay, and realize that the normal force is mg, but I just went and did F equals ma. I said, okay, 5-step method, picture forces, okay, regular coordinate system, I didn't draw it, but y-axis would point up. So acceleration in the y direction is 0. So normal force points up, mg points down, so I get normal force is equal to mg. So that's what I get to put in right there. So here where I have mu sub kn, normal force is mg. So I can take equation 2 and put it back into number 1. So here I have F sub kx. So that's mu sub k times n. Oops, I forgot the x. Don't forget the x right there. Got to put the x in there. Okay. And then mass drops out. All right. And then when I solve this for mu sub k, okay, solve it for mu sub k, I still have an x on the bottom. Oops, there's my x. All right, and that's the exact same thing that we got in the last chapter using F equal ma for the whole problem. So we just used that general expression, which already has, we used F equal ma in kinematics to derive this whole expression. Okay, so yeah, I did have to draw forces, okay, because we had the, we had the work done, where'd it go? We had the work done by a non-conservative force, okay, but I didn't really need to have a coordinate system, okay, so I just looked at the initial energy state, final energy state, and realized that the energy changed because I had a non-conservative force that did work.